I'm going to begin by talking about using secure protocols. Network security is always an ongoing process because the threats to it keep changing. Although security threats are continually evolving, administrators can use some techniques to harden the base network structure to help ease the ever-shifting security landscape. These hardening techniques establish a good security foundation that can be further built upon, making the network that much harder to crack. One of these hardening techniques is to use secure protocols whenever possible. So let's discuss some of those protocols. First up is Secure Shell, or SSH. It's a protocol that is used to create an encrypted communications session between devices. It's commonly used to create a secure virtual terminal session. It should be used in place of Telnet whenever possible. Then there's SNMP version 3. That's Simple Network Management Protocol version 3. It's a protocol that's used to manage and configure devices remotely on the network. It's more secure than the prior two versions because it supports encryption. Secure File Transfer Protocol, or SFTP, should always be used in place of FTP. It's a protocol that's used to transfer data and manage file structures in a secure manner through the use of an SSH session. As I said just a moment ago, it is a better option than FTP, which requires user authentication but does not encrypt the communication. SFTP encrypts the whole process. Then there's TLS, or Transport Layer Security. It's a cryptographic protocol that's used to encrypt online communications. It uses certificates and asymmetrical cryptography to authenticate hosts and exchange security keys. It is a better option than SSL, or Secure Socket Layer, which functions in a similar manner. When performing sensitive online business, you should use HTTPS, Hypertext Transfer Protocol Secure. It's a protocol that is used to secure the communications channel between a web browser and a web server. HTTPS uses either TLS or SSL technology. IPSec, or IPSec, is a network layer IP security protocol suite that can use multiple methods to mutually authenticate both ends of the communication channel. It also will encrypt all data transmissions. Unlike most other protocols, it can provide end-to-end security for any application. Let's move to using anti-malware software. Anti-malware applications help to protect networks and network resources against malware intrusions, as in spyware, viruses, and worms. There are three main options for using anti-malware applications. There's host-based anti-malware. The application is installed on the individual machines and only protects those nodes on which it resides. It's easily tuned to the needs of the individual host, but requires that the user keep it up to date. Then there's network-based anti-malware. The application is installed within the local network and served to the individual clients that require it. It is easily administered, but harder to tune for the individual hosts. But the network administrator can ensure that it remains up to date. And finally, there's cloud-based anti-malware. The application resides in the cloud, so it is outside of the local network. And it is served to the clients inside the local network as needed. This service has a very small footprint on the local machine and tends to be kept more current than the other options, but it is an added cost that must be evaluated. Let's conclude with talking about implementing switch and router security. When is using a password not secure? Well, the answer is when the password is kept in clear text. One solution to this is to save passwords and other sensitive information as hashes. Hashing is a cryptographic process that uses an algorithm to derive a set value, also known as the hashed value, from the sensitive data. The hash can be used to verify that data is coming from where it is supposed to and that it has not been intercepted or changed in transit. The most popular hashing algorithms are MD5 and SHA or SHA. Of the two, SHA is the more secure. And the wise network administrator makes sure that all passwords and usernames are kept as hashed values. Under implementing switch security measures, switch port security measures are vital. First off, switch port security should be enabled. All enterprise switches are capable of having security measures enabled at the port level, and that should happen. Also, the native VLAN should be changed from its default value. All active ports should be assigned to non-native VLANs. All non-active switch ports should be assigned to an unused non-native VLAN. Also, VLANs should be created to clearly segment the network into logical, secure areas. A switch port security measure that should be considered is MAC address filtering. This will only allow specific MAC addresses to connect to specific ports. DHCP snooping should be enabled. This will only allow DHCP responses from an administrator-defined switch port. This means that all DHCP responses will come from the same port. In addition to DHCP snooping, dynamic ARP inspection, or DAI, should also be enabled. This process is combined with DHCP snooping to restrict the opportunity for ARP cache poisoning to occur. All address resolution protocol requests are compared against the ARP table contained in the administratively defined DHCP server. Implementing these measures will greatly increase the security of your switches. Let's move on to router security measures. Each interface on a router should have an access control list, or ACL, in place to control and filter traffic. Each interface can actually have two ACLs. One ACL on the inbound side of the interface and one ACL on the outbound side of the interface. An ACL is a set of rules that is used to govern and filter the flow of network traffic into and out of a network. The ACL examines packets against its established rules, beginning from the first rule at the top of the list and continuing down through all the rules. The rules either allow or deny the packet from continuing. Once the packet matches a rule, the rule is enforced and the ACL process is exited. ACL rules can be based on protocols and ports, IP addresses, source addresses, destination addresses, etc. All ACLs end with an implicit deny statement, meaning that if it isn't specifically allowed, then the packet is discarded. The ACL can be time-based, as in day of the week or time of day, and it can fulfill a specific function based on the reason that it is created, as in an ACL can be used to filter out websites or web content. I'm going to begin by talking about encryption basics. Encryption is the process of taking a message and scrambling the data so that it can't be read if it gets intercepted. Encryption relies upon the fact that the receiver of the scrambled data has the proper key that allows it to unscramble the data and put the message back together. The strength of the encryption is usually determined by the strength of the key. The strength of the key is measured in the number of bits that it takes to generate the key. The more bits that it takes, the stronger the key is. There are two basic types of encryption. There's symmetrical encryption, in which both ends of the communication channel use the same key to encrypt and decrypt the message. Pre-shared key, or PSK, is symmetrical in nature. Then there's asymmetrical encryption, in which two different security keys are used in an arrangement called PKI, or public key infrastructure. The private key encrypts the message and the public key decrypts the message. On the return side, the original receiver encrypts with the original sender's public key, which then gets decrypted with the private key. In this arrangement, the private key cannot decrypt what it encrypted, and the public key cannot decrypt what it encrypted. So it only works if there are two separate keys. So let's talk about those asymmetrical encryption keys. There are two main types of asymmetrical encryption keys. There is the EAP TLS type key, that's Extensible Authentication Protocol Transport Layer Security type of key. It requires the use of a certificate authority, or CA, that is trusted by both parties. The CA provides the certificates to both parties that allow for the generation of both the public and private security keys. It's very secure, but it is also difficult to manage and maintain. Then there's TTLS, Tunneling Transport Layer Security. It's as secure as the EAP TLS, but only the authentication server receives a certificate for the key generation process, and it's easier to manage and maintain than EAP TLS. With that covered, let's move on to wireless network hardening. Wireless networks can represent a special challenge in the network hardening process. The goal of most hardening techniques is to keep nefarious elements from ever seeing the network traffic. But with wireless networks, that is all but impossible, as traffic is broadcast over known radio frequency channels. This traffic is subject to capture, and the transmissions inform any who care that an active wireless network is present. There are steps that can be taken, as in encrypting the traffic, to make sure that even if the network traffic is captured, it cannot be read. This helps to keep the network traffic safe and the network from being breached. One of the first techniques that you can use to harden a wireless network is MAC address filtering. MAC address filtering can be used to limit which devices can connect to the wireless network. If an unknown MAC address attempts to connect to the network, it is ignored by the wireless access point. So when it requests to join, the WAP checks its MAC filter, and if that MAC isn't in the filter, it just drops that requester. While MAC filtering can be effective, it can also be difficult to manage, and it is also possible to spoof MAC addresses. Which brings us to basic authentication and encryption for wireless networks. First up is WEP, or Wired Equivalent Privacy. It's an encryption standard that uses either a 40-bit or a 128-bit encryption key and the RC4 algorithm to authenticate devices and encrypt transmissions. It uses a pre-shared key as a password or passphrase to authenticate users. WEP is easily cracked and should not be used. As a matter of fact, WEP can be cracked in minutes. Better than WEP is WPA, Wi-Fi Protected Access. It's an authentication and encryption standard that improved upon WEP, but still uses PSK and the RC4 algorithm. But to increase security, it also introduced Temporal Key Integrity Protocol, or TKIP. TKIP generates a new security key for every packet, and that new security key has a strength of 128 bits or greater. Now, it's not as easily cracked as WEP, but it can still be cracked and should not be used unless absolutely necessary. And hopefully that's not the case in your wireless network. Better than WPA is WPA2 Personal, Wi-Fi Protected Access 2 Personal. It's an authentication and encryption standard that improved upon WPA. It does not rely upon the weak RC4 encryption algorithm, but it does use AES as its algorithm. That's Advanced Encryption Standard. It can also use the PSK method, but this is not required, as WPA2 Personal can also dynamically assign security keys. While it's theoretically possible to crack WPA2 Personal, it would be extremely difficult to do so So this should be the minimum level of security on any wireless network. Better yet, if possible, deploy WPA2 Enterprise. Now this forms a portion of the 802.1x standard. It is used to authenticate users on a wireless network and uses one of the forms of the extensible authentication protocol in setting up the encryption. A central authentication server is required for 802.1x or WPA2 Enterprise, which does allow for greater control over the authentication process. As a side note, EAP is actually a set of definitions for how security keys will be exchanged in order for encryption to take place. It's time to conclude with a brief discussion on security policies. While security policies are only written documents, they can actually do quite a bit to harden a network against a breach. Security policies document or outline what is allowed or not allowed to occur on the network from a security point of view. They are usually crafted at the upper layer of management with the help of knowledgeable IT personnel. They establish the expected behavior, which can go a long ways towards hardening your network. Security policies give administrators the authority to put into place measures to protect the security of the network. In many cases, they also give administrators the authority to enforce the policies that lead to a hardened network. Well, I'm going to start by talking about user authentication. Hardening the network will not do you any good if there is poor authentication of the users and devices that are allowed on the network. The process of proving that you are who you say you are, if you are a person, or that you are what you say you are, if it's a device, is called authentication. Authentication is different than authorization. Authorization is what you are allowed to do after you have been authenticated. There are several different ways in which users can be authenticated, and there are several different methods in which authentication can be implemented. Let's talk about basic authentication of the user. There are three basic factors for authenticating users. There's by what you know. This is the user and password method. By what you are. This is commonly implemented through biometrics. And finally, there is by what you have. This is commonly implemented through the use of security tokens. These are the three basic factors for authenticating users. Now you can combine these in a process that's called multi-factor authentication. That's requiring the use of more than one of the factors of authentication, as in requiring a password and a fingerprint scan, or the code from a security token and a password. Those are multi-factor authentication. Now, multi-factor authentication is used to increase the security of the authentication process. You might also implement a single sign-on process. It's a process in which the user only has to provide authentication once via a single smart device rather than having to authenticate for each and every network resource that they request. So let's talk about authentication and authorization methods. The first method we're going to talk about is PAP, Password Authentication Protocol. When logging into a network resource, the user or device is required to supply a username and password. The username and password are sent in clear text format, so this method is considered unsecure and should only be used as a last resort. More secure than PAP is CHAP, Challenge Handshake Authentication Protocol. It is similar to PAP in that when logging into a network resource, the user or device is challenged to supply a username and secret password, and it authenticates through a three-way handshake process. The way it works, the resource issues a challenge. It wants to know the hashed value of the username and secret password. The user's device sends the hashed value to the resource device. The resource evaluates the hashed value and either accepts or rejects the connection. By using CHAP, The username and password are never sent in clear text. It's much more secure than PAP. There's also MSCHAP. It's functionally the same as Challenge Handshake Authentication Protocol, but it is Microsoft's proprietary implementation of it. You might also implement one of the forms of Extensible Authentication Protocol, or EAP. It's not a single protocol on its own, but a set of additional authentication methods used by remote access clients. Currently, there are more than 100 different methods defined by the EAP specifications. One of the more popular is Kerberos. So let's talk about Kerberos. It's an authentication protocol which uses TCP or UDP port 88 by default. It's a system of authentication and authorization that works well in environments that have a lot of clients. The main component of Kerberos is the Key Distribution Center, or the KDC. The KDC has two parts, the Authentication Server, or AS, and the Ticket Granting Service, or TGS. Here's how it works. When a user logs in, a hashed value of his or her username and password is sent to the Authentication Server. If the AS likes the hash, it responds with a ticket granting ticket and a timestamp. So it will respond with a TGT that also has a timestamp. The client then sends the TGT with the timestamp to the Ticket Granting Service, the TGS. The TGS then responds with a service ticket, which can also be called an access token or just a token. The service ticket authorizes the user to access specific resources on that network. As long as the TGT is still valid, the TGS will grant additional authorization by issuing a new service ticket as required for as long as the TGT and its timestamp are still valid.